Hey, we have a pretty full day, and we're going to be looking at density as the first thing that we're going to start thinking about doing. And density, we're going to see that next unit we talk about density again when we start talking about properties of matter. But density of a substance is just the mass per unit of volume. And units of density are just like they sound, mass per unit volume. So if we think about this is a formula that you guys maybe want to have memorized, but what we're going to see is we can even use dimensional analysis again, and it will work out, and you don't really have to have it memorized, as long as you know some common units for mass and volume and density. So mass, it's the amount of matter that is contained in any object. You don't have this necessarily in your notes, but it's the amount of matter that's contained in any object. Wherever you are in the universe, it's always going to be the same. No matter if you're on Jupiter or Earth, it's always the same, that mass, how much matter is contained. Metric units that we would expect, what we're most likely going to work with is grams. That's something you should have a good understanding of, that grams is a unit of mass. Okay, next one, we have volume. And there's going to be a couple different things, ways that we can measure volume of a substance. One way is through direct measurement. If you have a solid object that's got a definite shape to it, like maybe a cube, you can do length times width times height, so that's pretty easy for us. You could do volume displacement for an irregularly shaped solid. We're going to see that's what we do in lab the next time we meet. So you guys can do a volume displacement method. I'm not going to go into that. It's part of your lab, and I think you guys have done that probably at some point in the past. And then another way would be through direct measurement if it's a liquid, and you would use a graduated cylinder for that. So some examples of units of volume that we would expect to see would be things like cubic centimeters, liters, milliliters. All of those are good examples of volume. And then, of course, yesterday we learned this unit conversion that we are still expected to memorize, and that's 1 milliliter is exactly the same thing as a cubic centimeter. All right, so then we get to density. Because it's mass per unit volume, you would expect units to be things like grams per cubic centimeter, grams per milliliter, grams per liter for a gas, because we're talking about particles that are spread out a lot more. Usually we use grams per liter. But anything where you have mass in the numerator and volume in the denominator. So that's our formula. We are going to use dimensional analysis when going through this. Don't forget about your correct units. You don't have this on your notes, but just ever so quickly thinking about what density means, and again, this is going to be really more of Unit 2, but thinking about these two substances. If I have block A and block B, and you can see there's different number of particles that it's made up of. So which block has a greater mass? A has a greater mass. Which one has a greater volume? They're the same. So we're seeing that the exact size of them I'm showing is exactly the same. So which block has a greater density? What would you say there? A, because there's a greater mass per unit of volume. Okay, what if I take one of these and I cut it in half? So what is the relative density of each of those halves? It's the same, so make sure you're not telling me it's half of what it was before. It is the same, and that's because it's that ratio. Not only did you half the volume, you also halved the mass. And we could go through some of these things. Which one has a greater density, a gallon of feathers or a gallon of gold? Gold, right? A lot more mass per unit volume. What about a greater volume, a gallon of feathers or a gallon of gold? Same, a gallon is a gallon. Greater volume, a pound of feathers or a pound of gold? The feathers would, in order to get a pound of feathers, you would have to have a huge volume of them. You don't have to have much gold for that. And then last one, what has a greater mass? Gallon of feathers or a gallon of gold? And gallon of gold has a greater mass. Okay, good. So now we get to the examples that you guys have in front of you. And what I would really like to see on these is I would like to see you doing this in dimensional analysis. Now with that said, this first one is really kind of tricky to even do in dimensional analysis. We know that our formula for density is mass divided by volume. And we read through here, and it says, a block of wood measures 2.5 centimeters times 4.6 centimeters times 1.6 centimeters. Its mass is 71.3 grams. Calculate the density of the wood. Now, I'm going to write down some stuff here. Do I know my volume? Yeah, I can figure it out, right? It doesn't really spell it out for me, but I can figure it out. You guys know what to do there. Anybody plug that in ever so quickly? Okay, so 150.88 cubic centimeters. Now, I'm going to go back to what we talked about with sig figs that first day of our notes. And we said when you have a multiple stepped problem, just keep it all in your calculator and round at the end. There's really no sense in trying to take that and round that to 151 this early on in the game. If it was our final answer, maybe we'd do that, but it's early on. So let's just keep it long like that. I'm going to use this information right here for when I determine my final significant figures for my final answer. But right now, I'm going to go ahead and just keep that in my calculator. So that is my volume. All right, I know my mass also, it's given to me. I just need to be able to, even if it didn't say this word right here, if it said you had a 71.3 gram block of wood, you need to know grams is telling you mass. So 71.3 grams. This is just as easy as you think it is. All you have to do is say mass, 71.3 grams, divided by volume, 150.88 cubic centimeters, equals, and you do the math. The only thing that really makes that dimensional analysis in this case is that I am making sure that I show my units in that math process. So I see that grams and cubic centimeters don't cancel out, so I have to stick with both of those as my final answer. Grams per cubic centimeter, exactly. That'll be my final answer. We'll have those units. And in my calculator, it gives me something like that. But then I know I'm going to round that to how many sig figs? 3 sig figs, so it becomes 0.473 grams per cubic centimeter. All right, I'm going to keep going with these because I want to make sure we have time for the working with graphing density on our calculator. Okay, next one says how many cubic centimeters are occupied by 75 grams of zinc if its density is 7.14 grams per milliliter. So the question is, again, we know density is mass per volume. Well, let's go ahead and identify the different parts that we have in this. If I see grams, what unit is that telling me? Mass. And then density, it tells me this is density right here, grams per milliliter. We're looking for volume. Maybe in your head you're changing this around algebraically. I'll do that in a second. But right now I know that I'm starting with grams and I'm starting with grams per milliliter. Do you want to start with 1 unit or 2 units? 1 unit, right? Remember when you're given the option of 1 unit or 2 units, always start with the 1 unit because we're not sure what's going to happen with those 2 units. So here I've got 1 unit. Here I have 2 units. Ooh, that's intimidating. Let's hold off on the 2 units and just start with our 1 unit of 75 grams. Now, pretend you have that brain cramp and you just can't figure out what the formula is for density. You don't know any of this stuff, and I'm hiding this with my hand right now, but you don't know any of this stuff over here. That's okay because dimensional analysis is going to get you through it. You want to make sure you get your answer as volume. In other words, we're going to try and get our answer, let's say milliliters is what we're trying to go for, right? So I want to get rid of grams and go to milliliters. Well, I can use this conversion factor right here. Which one goes on top? What number goes on top? 1. Because I know that I've got 7.14 grams, that's on bottom, for every 1 milliliter. So that's how dimensional analysis works with this. And I see that my grams cancel out. I'm left with milliliters, which is what I wanted. Suppose you were just doing algebra on this, and you take this formula, density equals mass divided by volume. Could you algebraically change that around, multiply each side by volume, and then divide each side by density? Sure, that's exactly what we did. Mass divided by our density right here. So that's exactly what we did. But we didn't have to make sure that we knew how to do this algebraically. We didn't have to have anything memorized. The units talked us through it. So that made it so perfect. All right, you know, I'm going to take this one more step because we're talking, not that you'd really have to, it would be okay, unless you were, ooh, no, it's not okay. It asks for cubic centimeters. So we have to take this one more step. And we want to get this to cubic centimeters, so milliliters go away, cubic centimeters up here. That doesn't trick you guys, you know, 1 to 1. So there we go. And our final answer, I'm just going to be the calculator here. It is 10.5 cubic centimeters. All right, you've got a few of those on your homework to work with. All right, let's see if we have questions here. Okay, so moving on. We're now going to get to graphing density, and this is not on our calculators yet. I'm going to do a different video, I think, for the calculator graphing. But when we plot this, and you're going to see that this is part of your first lab that you have to do. When you plot a line, it's known as the slope, and you guys know that. So the slope of a line is your rise over run. It's also known as the change in y over the change in x. So we're looking at density. Density is mass over volume. There is our rise over our run. So the slope is the change in your mass over the change in your volume, is what you would expect. Here it says when plotting mass on the when plotting these, this is what you're going to do. Mass is on your y-axis and volume is on your x-axis. So when you plot it like that, you're going to see that if you have a slope like that, that's your rise over run, the change in your mass over the change in your volume. So it illustrates the density of a substance. Here are some rules for a good graph, and again, I'm going to talk about this when we see our lab write-up. You must always throw in a title. Even if I don't specifically ask for it on a lab, you need to do that, because what's going to happen is I have a grading rubric, and it's going to say, hey, if they don't have these different things, it's -2, -2, -2. So you don't want to get those points off. So a graph should always have some sort of descriptive title. You could even call it density of lead, something like that, or mass over volume of lead. Label each axis and specify the units. So you would need to label your mass and volume, grams and cubic centimeters. Make sure you choose an appropriate scale. You know, you're going to see that going by 2s or 4s or 5s, depends on what you're looking at, but those are appropriate scales. Don't go by 3.5, you know, just making sure that you choose an appropriate scale. And as long as we're thinking about this, actually it's not on here, it's on the lab write-up, as part of that appropriate scale, it needs to be big. You're not making a little postage-sized graph. It's going to be big and cover your lab notebook page. So here's the thing about lab notebooks, is that you're working with these carbon copies, and it's really easy to then maybe do some other homework on top of that lab notebook and forget that it's going through to the other pages. So it's easy to get little marks all over the lab. You'll just learn to be conscious of that. But do your best to be aware of it, and eventually what's going to happen is you'll get these little marks on your paper. So when you are graphing, specifically put a dot with a circle around it. So when I graph something, that's how I'm going to graph it. I'm going to show that data point like that. That way I know it's not just some sort of little stray mark that happened to occur. We're going to make it real obvious that that is a data point on a graph. And then when you get all of these data points, what we're going to see is we have a best fit line. You're not going to connect the dots. You're not going to freehand that best fit line. I happen to have a drawer full of rulers over there. You guys can find straight edges with binders, whatever it is, but use some sort of straight edge to draw a best fit straight line. And then quite often you'll have to do some sort of calculation of that slope. And then we report the equation for the line as this. Here's something, our equation for a line is y equals mx plus b. Here's what I'm going to tell you now, and I'm going to tell you again when we go over our lab next time we meet. I want that equation for a line written in scientific, that's not how you spell it, scientific, there we go, scientific form. And what that means, and put a big star by it, because this is one of those things that even at the end of the year, I hear students going, oh, what does scientific form mean? What does that mean? It means at no point do I want to see a y and an x written down. I want you to define those variables. So if we're talking about graphing density, what am I going to define? What's my y? Your mass. So what you need to do is say mass, or if you want, you could just do the big capital M, equals, and then you're going to plug in a number for your slope, your M. And instead of x, you're going to say volume, or maybe a big capital V, plus whatever value you get there. So what scientific form means is that you define your x's and y's. You don't throw in an x and a y. You actually tell me what they are. All right. That's what this is telling you right here. Either way. So the question is, can you write big capital M and V, or should you write them out? And I'm fine with either one of those. Okay, so you know what? I'm not going to spend time on this other than knowing that we can look at these a graph, and you can read off different points on this. So if I was given volume, maybe this point right here, I could come in and come on up here and figure out what my mass is at that certain volume. And I'm jumping around in here, but since I happen to have these data points, if I was asked to figure out what the mass is of 25 cubic centimeters, it's not on a certain data point. So that example happens to be known as, anybody know? I'm going to write slowly. The process of trying to figure that out, I'm hearing it softly, interpolation. So the process of interpolation is figuring out some sort of data point between 2 points. Whereas if I was asked, and this is not a very well drawn graph, but I freehanded it like I should not, but let's pretend it looks like that, and I'm asked to figure out what is the mass at 45 cubic centimeters, well, I'd come on up here and go on over, and I would say, well, that looks like 225 grams. What's that process called? We've got interpolation, so this one is we're going beyond, exactly, extrapolation, we're going beyond, we're going extra, beyond the last data point. So that's extrapolation. Those are two words. That's not on your notes, but I think you should be familiar with those terms if you happen to see those. Inter is between, extra is beyond. All right. I'm going to skip all that, and I am going to end this video, and there will be another video that shows how to use your calculator.